Hello, I am Professor Narendra Kumar Pandey from Physics Department, University of Lucknow. And in my lecture series on lasers, this is my 13th lecture that I'm going to deliver today. And the topic for today's lecture is the effect of diffraction and reflection on field pattern. Actually, in any resonator system, because the beam moves or oscillates to and fro between the two mirrors of the resonator, then in going from one mirror to the other, the beam has to suffer diffraction. And on reaching the mirror, it suffers reflection. So naturally, this diffraction and reflection has got bearing on the beam in the cavity resonator. So before we go for the actual cavity resonator mechanism, let us understand first of all effect of diffraction and reflection on the field pattern in an optical resonator. So let me welcome you first to this lecture and then let us start. So you see, the figure shows a set of two mirrors, and as we have seen in the very first lecture of the resonator system, that an optical resonator consists of two mirrors, and these two mirrors could be of different types. It could be concave convex combination, it could be concave concave, it could be plane and concave, it could be both the plane mirrors. So various types of combinations are used as optical cavity resonator system. And in this, when the beam is oscillating between the two mirrors after having stimulated emission, when the atoms are pumped to the higher energy level, and when they come back to the lower laser level because of the stimulus photon given from outside, then the beam that is there in between the resonator, that oscillates or that moves between the two mirrors. So when it moves between the two mirrors, and if a particular field distribution of the beam is repeated in one round trip, then this particular field distribution will be called a mode of oscillation of the cavity resonator. So by mode we mean the repetition of the field pattern. Otherwise, if the field is not repeated, it means that has suffered destructive interference, and because of that, that is lost. So here, a mode of the cavity is a field distribution which is such that after one complete round trip through the resonator, the resultant field distribution is the same as the distribution we had started with. Now, for this, we will consider first the effect of diffraction on a beam between the two mirrors. We have shown, the figure is showing two such planes. Now this is an x dash y dash plane, and this is an xy plane. So we consider a plane wave that is incident normally on a diffraction aperture. This is a diffracting aperture. And this diffracting aperture is lying in the plane x dash y dash, and the field will be seen in the plane xy. So what we have, that we have an aperture in the plane x dash y dash, and on this aperture a plane wave is incident normally. Naturally, when the plane wave arrives on the aperture, then according to Huygens principle, each point of this aperture is going to behave like a source of secondary disturbance or wavelets emitting fresh waves. And when these waves from the aperture, they propagate in the medium, then from different parts of this aperture, the wavefronts that come out, they superimpose in the space. They superimpose everywhere in the space wherever they reach. And we consider one such point, that is Pxyz in the plane xy. So this we call the field plane. Here we have the source plane, and here we have the field plane. So we have this as aperture A, And this is origin O dash, this point is Q, and this point is P. This distance between P and Q we have taken as R. Here the origin is O, and this point is P, X, Y, Z. So now again, let us consider a plane wave incident normally on a diffraction aperture A. The field at point P can be calculated approximately by using Huygens principle, according to which every point on a wave front is a source of secondary disturbance, and the secondary wavelets from different points mutually interfere. So, field at point P due to spherical waves spreading out from elementary area dx dash dy dash. We have taken an elementary area. This point around this point Q, we have taken an elementary area. Let us say dx dash dy dash. So, field at point P due to a spherical wave spreading out from elementary area dx dash dy dash around the point Q x dash y dash 0 should be proportional to a to the power of minus I k r upon r dx dash dy dash. Now, here a is the amplitude of the wave in the plane of the aperture. Mind it, we have taken in the plane of the aperture the amplitude of the wave as a by r, and this amplitude will vary as a by r. We have taken the amplitude a, and the amplitude will vary as a by r. As distance increases, so the amplitude will decrease. And this distance r we have taken as the distance between Q and P, and this can be written as x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square to the whole power half. R represents the distance QP. So the field at point P due to the entire aperture, that is, if we consider the entire aperture and then we divide the whole aperture into elementary areas like dx dash dy dash, and then this is the field because of one such elementary area, then because of all the elementary areas that the aperture constitutes of, the field will be given by the sum of the contribution to the field by all such elementary areas. That is, of course, by integration. So field at P due to the entire aperture can be written as G at P is equal to C double integral over the aperture A amplitude exponential minus I k r by r dx dash dy dash. Here C is the constant of proportionality, which can be determined by noting that in the absence of aperture, the field at point must be equal to a to the power of minus I k z. Naturally, you can understand that if there is no aperture, then the plane wave that we have considered, this would propagate as it is and would reach this point. And we know that in a plane wave, the amplitude remains constant as the wave propagates in the medium. So, C is the constant of proportionality, which can be determined by noting that in the absence of aperture, the field at point P must be equal to e to the power of minus I k z. So, C double integral over the aperture A exponential minus I k r by r dx dash dy dash should be equal to, of course, A e to the power of minus I k z. If we carry out the integration under the approximation that most of the contribution to the integral comes from the domain x minus x dash, y minus y dash, which is very, very smaller than z, we can get C is equal to I upon z. And therefore, the field at point P can now be written as G at P is equal to I by lambda double integral over aperture A exponential minus I k r by r dx dash dy dash. So let the amplitude and field phase distribution on the plane be x dash f x dash y dash z. We suppose that the amplitude and phase distribution on the plane be considered as f x dash y dash 0. In most of the problems of practical interest, the dimensions of the aperture is very, very small. So that r does not vary appreciably over the area of the aperture. These apertures are very, very small, and therefore r will not vary much over that aperture. Hence, very little error will be introduced if r in the denominator is replaced by z and taken out of the integral. And that is how we can write down z at p. And because we have taken out this r outside, so we can write down g at p. This r we have taken out. So z at p is equal to I by lambda z, that r has become z, and double integral over aperture A, f x dash y dash 0 e to the power of minus I k r dx dash dy dash. So r can be written as, if we take z out of the square root, then it is 1 plus x minus x dash whole square by z square plus y minus y dash whole square by z square power half. So z, if it is introduced inside with the binomial expansion, because we have considered that the contribution is very, we have supposed here one particular point, that this point I'm talking about, if we carry out the integration and the approximation, most of the contribution to the integral comes from this, which is very much smaller than z. If we repeat this over here, then we can say that r can be written as, that is r is equal to z, and the square root of 1 plus x minus x dash whole square by z square plus y minus y dash whole square by z square power half. A binomial expansion can be made out of this, and therefore r could be written as z plus x minus x dash whole square by 2z plus y minus y dash whole square by 2z by expression 8. Therefore, if we substitute this value of r in the expression for gp, then g at x y z can be written as I by lambda z e to the power of minus I k z, because if in the r we take this particular z, then r minus I k z will come out of the integration as a constant, and inside we have f x dash y dash comma 0 exponential minus I k by twice z x minus x dash whole square plus y minus y dash whole square and dx dash dy dash. This is how we can write down the field at x, y, z. So this expression 9 represents the effect of diffraction by the aperture on the field. Now, next point is, let us consider the effect of a mirror. In the figure, I have shown a concave mirror, and this could be a convex mirror also. This could be a plane mirror also. Now we have a concave mirror over here, and we have a point source P that is placed at here. We have a point source P. Now, at a distance u in front of the concave mirror, and the radius of curvature of this mirror is r. You can see this r is the radius of curvature of the mirror, and center of curvature is at C. Now, naturally, because P is the object point, and therefore the divergent spherical waves will come out of this and move toward point A. The mirror will change this divergent spherical wave fronts into the convergent spherical wave fronts, so that they converge at the image point Q, whose distance from the mirror is taken as V. So this divergent spherical waves are converted to convergent spherical waves, and they converge at point Q. So P is the object point, Q is the image point, C is the center of curvature, this distance is U, this distance is V, and this radius of curvature is R. Now we know the formula, 1 by V plus 1 by U is equal to 2 by R. So we can write down 1 by V is equal to 2 by R minus 1 by U. The mirror converts an incident diverging spherical wave of radius of curvature U to a converging spherical wave of radius of curvature V. The phase distribution in the transverse plane AB of the incident diverging spherical wave. What will be the phase distribution in the transverse plane AB? When the incident diverging spherical waves are coming, then what will be the phase distribution in this plane, very close to the focus? What will be this? The phase distribution in the transverse plane AB of the incident diverging spherical wave is exponential minus IK by twice U x square plus y square. Of course, this is apart from a constant phase term. Similarly, the phase distribution of the reflected converging spherical wave on the same plane, that is AB, will be exponential ik by twice v x square plus y square. Now, this is the phase distribution at AB for the incident diverging spherical wave. And this is the phase distribution of the reflected converging spherical wave on the same plane AB. Then, if we consider that PM represents the factor by which the incident phase distribution is to be multiplied to obtain the reflected phase distribution, then we have PM multiplied by the phase distribution because of the incident diverging spherical wave is equal to the phase distribution in the plane AB because of the second part, that is the converging spherical wave fronts. So PM into exponential minus ik by twice u x square plus y square is equal to exponential ik by twice v x square plus y square. So PM is equal to exponential ik by r x square plus y square. Now mind it, very simply, we have two factors now. Number one, this is the effect of diffraction on the beam, making oscillation between the mirrors. That is, the field at point P, field point will be given by this expression, and because of reflection, this will be the phase distribution that will have to be taken into account. So if a beam is moving from one point to the other in between the two mirrors, diffraction will be given by expression 9, and because of reflection on the mirror, the phase distribution will be taken as given by the expression 13. Thank you very much for your kind attention. So these are certain references you can consult for this. And disclaimer is, of course, this content is exclusively meant for academic purposes and for enhancing teaching and learning.